In the second part, I want to talk about Quicksort, another efficient and well-known sorting method. And let's see if you know Quicksort already. The attentive student might recognize the options. The same as in the last question. I'm tempted to show the results early because it seems quite clear. Shall we do the 3, 2, 1? Let's put a bit of a competitive element in this. Yeah. So the first answer is correct, and vast majority got this. No. So in this formulation, split is, what does split the elements around is a bit vague, I guess. The other term that people, well, historically at least use for this is partition. Partitioning can mean many things, but okay, it's stuck here. And what we mean by partitioning here is again, here's a picture. You have an unsorted list that can have elements in an arbitrary order, and it's partitioned if there is an element so that to a certain at a certain point this element is located, and then everything to the left of it is smaller than this guy, and everything to the right of it is larger than this guy. Okay, so in that picture, this rectangle below that dashed line here has to be completely bright, and the rectangle up here has to be completely empty. That's another way to say it. There are different ways how you can do this. Smarter ways and easier ways and better ways and faster ways. I'll show you the kind of definitive way, I think. It's the way, essentially, how the original inventor described it, Tony Hoare, and is still the one that's used in most libraries, but it's not the one that is always taught because it's a little more finicky to program. But here goes. You start by picking a pivot element. That is the one that will eventually divide the two. So this will be the one that you want to put in here. And you can really pick any at the beginning, doesn't matter. And then you want to start with 2 pointers that walk towards each other. That's why it's also called crossing pointer technique. One is on the left end and one is on the right end. We'll come to that in a second. And so you compare this element to the pivot, and this is smaller, and it's on the left, so it's where it's supposed to be. So we can just leave it alone. So we go to the next one. This one's bigger, so this is not good. We have to do something about it. It has to go to the right-hand side. Now we could simply swap it with this one, but that would have been a mistake because that's also big. We don't know that yet, but we see it as a human. So instead the algorithm does something else. It now takes this other pointer that starts from the right and passes the control to this one. We compare this element with the pivot, and now we find this is big, so it should actually stay where it is, and we leave it alone. At some point we run into one that is smaller than the pivot, and now we have a pair of elements identified where the 2 pointers are. The one on the left is big and should go to the right. The one on the right is small and should go to the left. Well, that's a match made in heaven. So we just swap those two. Okay? And then we continue again with our pointer on the left. Keep going. So this is small, can stay where it is. This is small, can stay where it is. This is big, so it should go. Then we pass the control to the other side. This is big, so it can stay where it is. This is small, so it should go. Now we swap those two. And then once those two pointers point to the same position, that's our signal that we're actually done. And that has happened now. So there's one last step you want to do. That is putting the pivot between those two segments. Then we've realized this picture up here. As you may see, everything here is filled. Everything up there is empty. This is entirely filled. This is entirely empty. Beautiful drawing. A few things to note. We didn't need extra space. This was running in this original array that we were passed. So this is running in place. We visit each element exactly once with this pointer. So sometimes we keep it in cache for a while, but we only need 2 elements that we're looking at plus the pivot. So we don't really need to load and store the elements twice like in merge sort. And that's one reason why Quicksort is quick and deserves its name. And the last thing, just for using this method in sorting then, you have at the end of the partitioning, you have a pointer to the position where the pivot is. So you can return this one, and this information will be used then. I spelled out some concrete code for the partitioning method because, as I said earlier, this one is very finicky to properly implement and get all the details correct. It's no magic, but there's many things you can do wrong that have unthought consequences, where if you don't pay close attention, it screws up some cases. And I'm not saying this, well, this is not an academic perspective. All these mistakes have happened. So people made these mistakes, then people said, oh, my sorting method is very slow, but I'm just sorting this harmless list. And then people noticed, oh, if you sort a list where all the elements are equal, it goes quadratic, not great. Things like that can be avoided, so just take this method if you ever need to. But most of the time, you will have an implementation in your library. The overall picture then for Quicksort is spelled out here. Again, we have our recursion, so it's again a divide and conquer algorithm. But this time, the work is done first, and then the 2 recursive steps come as the last part. Unless we're already done, we choose a pivot, and we'll talk about this in a second, but it can be any element for now. And then we call the partition function that I just showed you, which returns the position where the pivot lands at the end, and then we recursively sort everything to the left of the pivot and everything to the right of the pivot. Okay? Now, at this point, there's a call to a method. Because choosing a good pivot for Quicksort is, again, a little tricky. You have to make compromises there. If you just pick a fixed position, like in the example, I picked the first one, that's actually a really bad idea. You can think about why. A much better idea is picking a random position, where you actually throw a dice and pick a random position. And even if that is just a cheap, approximately random position, it's already good enough. Or you can do something slightly more advanced. So you can take 3 elements and take the middle of the 3. What you want for your pivot is not to be very small or very big. I think we'll come to that, why that's the case. I probably gave the answer to this one away if you were listening very carefully to what I said. So same horrendous list of possible answers. What's the worst case running time of Quicksort? And yes, I realize for some of you this will be like, wake me up at 2 a.m. and I'll tell you. Was it last year that this was an exam question? I put it one. Why am I telling this? Okay, note to self, not this time. It was on the easier side of the exam questions, to be fair. Okay, 46, can we get the 50 full? But it seems quite clear. 3, 2, 1. So you have to scroll down all the way. So yeah, Quicksort has this annoying feature that the worst case is quadratic, which is, so just to be clear about this, is really, really bad. For sorting, that's way too slow. We don't want that. But it is what it is. I want to show you not a full analysis of Quicksort, but a nice connection that maybe you haven't seen and you might appreciate, and it nicely connects to the previous unit. So I really love this part. And then it allows me to comment on a few things. But it's also not very technical, so that's nice. Suppose we're sorting with Quicksort this list. And let's make some simplifying assumptions. We're always picking the first element as pivot, and the partition is not the one I've shown you, but a simpler one that is stable. You could basically ignore what I said. It's just nicer to show it that way. It works with the real partitioning one, but it's more convoluted. And I tried to push this under the rug, but I feel the little devil on my shoulder says me, I have to tell you. So here's a way that Quicksort could work. It picks the first element as a pivot. Then it takes all the elements in the list that are smaller than this pivot and puts them to the left. And it puts all the elements that are bigger to the right. And as you can see, it kept the relative order in this case, which our partitioning method would not do. But I've said enough about this. You can do it like this if you have extra space. That was the first step, though, but we have to recurse, right? So we do this one more time. There's another split, and we do this here, another split, and you keep going. So, and at the end, like these are all empty recursive calls then. If you connect the pivot elements, how they relate in the recursive calls. So there was the first step was using 7 as a pivot, and it had 2 child recursive calls for the left and the right part. And I connected those to the pivots that were used in these recursive calls. Okay, so clear what these lines are doing. Now let's do something that looks maybe unrelated first. Let's take this same list of numbers and insert it into a binary search tree. We start with inserting the 7. The tree is initially empty, so nothing really happens. The 4 is smaller than 7, so it has to go to the left. Now the 2 is even smaller, so it goes to the left of those 2. The 9 is bigger than 7, goes there. The next one, 1, has to bubble out down all the way down here, so it goes there. The 3 is smaller than this, but bigger than 2, so it should end up here, and so on. And you may note that the trees are the same. Okay, we get the very same shape on the left and on the right. And if you think about it, there's no magic going on. This is just Quicksort and binary search trees are very, very related, especially this variant of Quicksort. And yeah, some famous algorithms researcher John Bentley said Quicksort is like a binary search trees are like frozen Quicksort. Or the other way around? Well, it's a nice analogy that, in a way, a binary search tree is a snapshot from some time in Quicksort. So if you take the recursion tree of Quicksort, you get the same as if you build a binary search tree by just insertions. And this resemblance goes further. If you look at what comparisons you've done to build the tree, you do the exact same comparisons, just in a different order. So here in the binary search tree, you compare everything to the root when you insert it. And in Quicksort, you start with the first comparison for all elements in the first partitioning round by determining if it goes left or right. But it's the same comparisons, just reordered. So that means whenever you analyze Quicksort, you might as well think about binary search trees or vice versa. They're identical in their analysis. And that, of course, means all what I said about binary search trees last time is also true for Quicksort. In particular, if things come in this unfortunate order, then we get the linear depth and for Quicksort then the overall quadratic time. But also, I said for binary search trees, whenever there's some kind of randomness in the insertion order, you don't get this bad behavior. And the same is true for Quicksort. And here we're even more lucky than for binary search trees. For binary search trees, the best I could say was, it won't usually happen, don't worry too much. But you can't guarantee it. If someone deliberately says, I'm inserting the elements in sorted order into your binary search tree, then you have to do something about it. And one solution was to use a balanced binary search tree. In Quicksort, we have a different option. No one forces us to do the stupid choice of pivots from left to right, because that's what would give you this one if you start with a sorted list already. Instead, you can randomize the choice of the pivot, and then you enforce the average case for binary search trees. A cute way to do this is a good Quicksort implementation is first shuffling the input, destroying any order that might have been there, and then sort it again. Sounds a bit crazy, but it's actually a quite reasonable way to do it. Okay. You can say much more precisely what is happening in Quicksort and in binary search trees. Same thing as I said. For example, you can count the number of element visits, and the recursion is a little more tricky because we don't have the same sizes, even if you take powers of 2 as the input. So we'll skip the analysis here. But you can compute that it is 1.39 times n log n element visits on average. And it's often close to that. And you should compare this to the 2 n log n from merge sort. So you see there's a factor difference. It's just a constant factor, but it's quite significant if this is your running time. And you can prove much more precise statements, as I already hinted at in the binary search tree part. I think the intuition behind this is for Quicksort to be really slow, you have to not just one or a few times catch a bad pivot, which might happen, you can't avoid that, but you have to be constantly unlucky. And that's just more and more unlikely the bigger the list gets. So all of that just for background. What can we say about Quicksort? In the standard scenario of sorting that we're looking at here, it tends to be the fastest way to sort, or at least good variants based on it are the fastest. The average case is still n log n, even though the worst case is quadratic, as noted here. It's good that it works in place. That was the big blemish of merge sort. It needed this extra space. And again, the memory access remains sequential. The partitioning, again, is not jumping around in the array. So it has the same virtue as merge sort on this side. What we lose, apart from the bad worst case, is the stability. If you do partitioning without extra space, you lose stability. It's pretty much one or the other. You can't have both and have a simple algorithm. So that's one open problem in algorithms, is to find a simple algorithm that's fast in practice, is stable, and in place. If you give up any of these 4 things, there are solutions, but not for all 4. And the first one is a little, what is a simple algorithm, is a bit hard to formalize. But it would be nice to have a solution to this, or proof that it can't be done with some formalization of simple. But yeah, no one has come up with this yet.